Wait.
Recording is started. I'm going to let everyone in. Ready?
Okay. Good. Thanks. Hi, everyone. I'm just waiting for everyone to trickle in, and then we'll get started. Um, in the meantime, maybe let us know where you're joining us from. Um, I'm in Toronto. Um, yeah, and if you're a teacher, you can share what grades you're teaching. Just so everyone knows, if you're registered for this session, it will be recorded and sent out to you. Okay, awesome. I'm seeing someone from Montreal. I'm teaching grade 8. Oh, we have a teacher from Singapore here. Hello. Um, okay, welcome everyone. Awesome. Awesome. Welcome. Awesome. Okay, well, hi, I'm Daniella. I am an education specialist, I think is my title here at Discover the Universe, and I'll be leading you through this session about how you can measure the Earth with your students and the Eratosthenes experiment. Before we get started, oh, before we get started, I'd like to do a land acknowledgement. So, Discover the Universe, we are based in Canada and we're not specifically in one place, and our programming is global. As you could tell, we have people joining us from all over Canada, all over the world. Um, but I'd like to take a moment to acknowledge the land that we're on. So, I live in Toronto and I live and work and benefit from the traditional land of the Mississaugas of the Credit, the Anishinaabeg, the Chippewa, the Haudenosaunee, and the Wendat peoples. Currently, this land is home to many First Nations, Inuit, and Métis peoples. Um, this land was traditionally named Jitgurunto and currently is Toronto. And I recognize that I am a settler on this land, and as well as all the people here, we are treaty people because Toronto is covered by Treaty 13 with the Mississaugas of the Credit. Um, I recognize that I benefit from this land and I have an obligation to protect and respect this land. I don't know, I mean, I just asked you, but I don't know where you're all coming from many different places, but I encourage you to figure out whose land you're on, the history of the land, um, and to take a moment within yourself to acknowledge the land that you're on. Okay. I'm going to get started now. If you're unfamiliar with Discover the Universe, our goal is to help educators to teach astronomy, and we do this by providing resources, training, and so many other resources online. All of our resources are free and bilingual, and we are national. So please visit our website if you'd like to see some more of our programming and what we offer. Our next webinar is in November, and it's about how you can teach the solar system. So please register for these, check them out, and we hope you can make it to them. Okay, so getting started on how you can measure the Earth with your students. So I'll go into the Eratosthenes experiment and then how you can bring that into your classroom or into any space that you're teaching in. So basically, in summary, what you'll want to do is measure the shadow of a vertical rod on the day of the equinox. So the equinox itself is September 22nd, 2024. This is a Sunday, so you can do this with your students the day after on the Monday, or you can even do it on the Friday a few days beforehand. What you also have to do is use a web tool, which we will provide to you, to measure the distance between your school and another location on Earth. And I'll get a bit more into that as I keep going. And we will also be providing you with a Google Sheet that does all the math that I'll be explaining for you. So if you're not a math teacher, don't even worry. Say if you have younger students, totally okay. This Google Sheet will do all the math for you. Okay, so this project is really multidisciplinary. So the experiment covers mathematics, and you'll see that it is basically just using triangles to do really interesting calculations. It covers history because we're talking about an ancient Greek scientist who did this experiment and was able to very accurately calculate the circumference of the Earth. It covers geography. You'll be able to compare your location to another location on Earth. And of course, it covers astronomy. Also, you'll be collecting real data. So you'll be doing that measurement yourself. You'll have your vertical rod. You'll measure the height of the rod and the length of the shadow. There we go. You'll be reproducing a famous experiment from the past. And there's also the opportunity to engage in this experiment on an international project. So you can collaborate with another school to get results. And you do your measurement, another school across the world does their measurement, and you can compare your results through this international collaboration. Okay, so I'll go into Eratosthenes and talking a bit about who he was and what he did. So he was a Greek astronomer, geographer, mathematician, philosopher. He did so many things, but I think the best thing about him was that he was very curious, and he was very interested in learning and understanding things. And that's what led to this experiment that he did. He was the chief librarian at the Library of Alexandria as well. He made simple observations, and using geometry, he was able to calculate the size or the circumference of the Earth to amazing accuracy. So what he observed is that on the summer solstice, at the time of local noon, he noted that the sun was directly overhead in Syene, which is currently Aswan, and it actually lit up the bottom of the wells in that location. But in Alexandria, objects that were completely vertical, he noticed that there was a small shadow. So how could it be that in Syene, the light from the sun was going completely vertically down, but then in Alexandria there was shadows, meaning on these vertical objects, meaning the sunlight wasn't perfectly vertical. Okay, so this is kind of an image of what he observed. In Syene, the light was completely going straight down these wells, but in Alexandria, there was a bit of a shadow off of these vertical objects. And this was because of the curvature of the surface of the Earth. So I have a little demonstration like the one in the picture. Unfortunately, my background is blurring it out. But basically, you take a sheet, you can do this yourself. You take a sheet of paper, you put two little sticks on it. When you hold it flat and you point it at a light, you'll see the shadows are the same. But if you curve it slightly, one will change the shadow, one will change the shadow and the other one will stay the same. Or if you point one at the light, there will be no shadow and the other one's shadow will lengthen. So if you just have a sheet like this, oh, there we go. It's okay. You can see it from the picture. If you curve your simple model of the surface of the Earth, you can see how the shadows change. And so that was what Eratosthenes actually observed. If you want to see Carl Sagan do this demo, you can watch the YouTube video that's linked on this slide. And this is a bit more about Eratosthenes' observations explained. It should play. There we go. So you have in Alexandria, you have the vertical statue. In Syene, you have the well, and you see that the light is going straight down the well, but causing the shadow in Alexandria. Eratosthenes was able to use this to calculate different angles. So, and by calculating those angles, he was able to determine the circumference of the Earth. And now you're thinking, how can we use math to do that? I'll explain it. So that little angle that the light rays make with the tower in Alexandria forms a triangle with the shadow. So this triangle right here is the triangle that he's comparing to the triangle along the Earth. So this angle, the angle that the sunlight makes with the tower is the same angle that Alexandria makes with Syene. So he measured that angle to be 7.2 degrees. This is 1/50th of a full circle, which is 360 degrees. He notes that the Earth is a full circle, it's round, and so it covers 360 degrees. So this angle right here between Alexandria and Syene is 1/50th of the full Earth. And he knows that the distance between Alexandria and Syene is 5,000 stadia. Stadia is an ancient unit of distance. It's about equivalent to 800 kilometers nowadays in our units. And so he knew that the angle is 1/50th of a full circle. And that distance, the physical distance, is around 5,000 stadia. So he was able to do the calculation where 7.2 divided by 360 is the ratio of the angle to a full circle, the angle he measured to a full circle. And he's got 5,000 stadia as the distance, and he can determine the entire surface of the Earth, the entire circumference of the Earth, based off of this fraction. So again, the angle he measured divided by full circle equals the distance between the two locations divided by the circumference of the Earth. So he knew again that the angle he measured was 1/50th of the total circumference, or 1/50th of the full circle. So he could calculate the circumference by multiplying the 5,000 stadia by 50. And so he ended up getting a measurement of 250,000 stadia, which was equivalent to approximately 40,000 kilometers. And what we know as the circumference of the Earth right now around the equator is 40,075 kilometers. So he was off by only 75 kilometers with his measurements, like his ancient measurements of the circumference of the Earth. And all he used were his intuition, his observations, and simple triangle mathematics. Okay, so now I'm going to go into the experiment and how you can bring this into your classroom. Okay, so the conditions you'll need to be taking 2 observations from different locations on the same day. That's why the international collaboration is a good opportunity to have this. What you'll do is you'll want to take a measurement when the sun is at its highest point in the sky, so at the local noon. This is different from just like noon, 12 p.m. The local noon is the point where the sun is at the highest point. Oops, there we go. And the locations of the 2 observations need to be at the same longitude point, or at the same longitude. So every point on the Earth has a longitude, latitude. You'll want to find a place that is just further south or north of you along the same longitude line, as much as possible. Okay, so the steps for this experiment is, the first thing, you want to find the time of your local noon on the equinox for your location. Again, so the equinox is the 22nd, but if you're bringing this into your classroom or into a space where you're teaching, you will probably end up doing it on the 23rd or a few days before on the Friday. So on that day that you'll be doing this, you'll want to find the time of local noon for your location. Then you'll want to hold the stick vertically and measure the shadow that the stick casts at that local noon at that time. You'll want to also calculate or measure the angle formed by the shadow. So you'll have the vertical stick, you have the shadow, and you want to calculate this angle right here. I will go in, I see the question in the chat. I'll go into how to find your local noon, your solar noon for your location. I'm going to go through each one of these steps in more depth. So first step, you find the time of the local noon. Second step is you measure the shadow. Third step is you calculate the angle. Fourth step is you can collaborate with another school at a similar longitude through that international collaboration option. Or if you know someone at a school at a similar longitude, you can collaborate with them as well. Alternatively, if you're not doing that collaboration or you don't know anyone who's at a similar longitude, you can use the data for an imaginary school at the equator. So a school at the equator would measure an angle of 0 on the day of the equinox. And so instead of collaborating with another school, you would just input the angle of 0 for the other school's measurement. And then based off of your angle that you've calculated and the angle of the other school, or 0 in the case that you're not collaborating, you'll be able to calculate the circumference of the Earth. If you don't want to do the math, that's totally valid. I will go into the math a bit more later on. If you don't want to use the math, we do have a Google Sheet that we'll give to you where you just input your values and it'll do the math for you. It'll do those calculations. Okay, so now I'll go into how to find the time of your local noon or your solar noon. So again, you'll want to take the measurement of the shadow when the sun is at its highest point in the sky during the day. This will not be exactly at noon for many different reasons. So you'll want to determine when exactly that solar noon is, the local noon, when the sun is at the highest point in the sky. There we go. So I use an online tool that I'll talk about in a second to take this screenshot of the sky at noon, so just 12 p.m. on September 23rd, 2024 from Toronto. And you can see that it is not at its highest point. It's not, it will be at its highest point when it's in line with this middle line right here from south to north. It goes all the way across the sky. And you can see that right at noon, it is not aligned with that at all. So what you'll want to do to find your local noon, your solar noon, is you can use the NOAA solar calculator, where you move the red marker to your location. So I've moved it to Toronto here. You'll select the date. So here I have put the 23rd of September, 2024. And then your solar noon will pop up in the results section. And so in Toronto, the solar noon on September 23rd, 2024 is at 1:09 p.m. And it will, so yeah, 1:09 p.m., 42 seconds, around 1:09 will be sufficient. So for your location, you'll want to go into this calculator, select or move the red marker to select your location, put in September 23rd, 2024, and find the time of your solar noon. Then you can use Stellarium, which is the program that I was just using, or I took the screenshot of to show you that at noon, it's not the solar noon. So you can use the web tool, the stellarium-web.org, or you can download the entire application to determine where the sun will be at the solar noon. Okay, so this is just a screenshot when I opened the app the other day, but I went in, I put in September 23rd, 2024. I put in 1:09 p.m. and it shows that the sun is right along that line that I pointed out. You'll also want to double check that this is in fact the azimuth of the sun. So that is the point where it's at its highest point in the sky. If you click on the sun in this application, it'll pop up this info window, and you can double check that the azimuth is 180 degrees. And this is due south, but you'll just want to double check that it's the 180 degrees. Okay. So that's how you can find the time of your solar noon in your location on the day of the equinox. Now, for the second step, you'll want to measure the shadow of the stick. So at your time of local noon on September 23rd, you will measure the shadow of any stick. You can even use a water bottle if you'd like. Anything that can stand vertically on the ground. A suggestion for you is you can use a meter stick, or a plunger works really well as well. And you just you stand it up on the ground, and then you observe how the shadow of that object is cast into the ground, and then you measure the length of that shadow. There is an Eratosthenes contest, so through also the experiment website, the international collaboration, there is a contest, or there has been in previous years, there might be again this year. If you take pictures when you're doing this experiment, you can submit those pictures to possibly win the contest. If you want inspiration for how to do the measurements, there is also a gallery of photos on their website. Okay, so yeah, this is the second step. You're basically putting your stick vertically and measuring the shadow that gets cast onto the ground. Then you'll want to measure the angle that is formed by that shadow. Measure or calculate it. So you can use simple trigonometry to calculate the angle. Basically, if you remember from any of your math classes in high school, you'll have the tan of the angle, the tangent of the angle, equals the opposite side, so S side, divided by the adjacent side, which is the H side. So if you want to determine the angle, it is the angle equals the arctangent of the opposite side over the adjacent side. So in this case, your opposite side would be the shadow, and your adjacent side would be the height of your stick. So if you're using a meter stick, the height of your stick is 100 centimeters or 1 meter, and then you measure the length of that shadow. Another option, if you don't want to do the calculation, totally okay. You can use the Google Sheet, the one that we're providing for you. You just put in the height of your stick and the length of the shadow. It'll do the calculation of the angle for you. Alternatively, you can draw a triangle to scale of the height of the stick and the shadow, and then use a protractor to measure that angle. Or you can find out some other way to measure the angle directly when you're doing this. So there are applications on your phone that you can use as a protractor to measure the angle, or you could take a picture of your little triangle or of your setup and then measure it with a protractor on your phone later. There's many different ways that you can do this, as long as you get that angle, whether it's through calculation or you measure it yourself. Okay, then you'll want to use the data from another location, say you're collaborating or you're using the imaginary school at the equator. Once you have the angle for your location, you'll want the angle from another location. And so the two options, again, are collaborating through the Eratosthenes experiment to match with a school at a similar longitude. Or again, use the imaginary school at the equator, and you use the value of 0 for their angle. So Why do we do this experiment on the equinox? Why would we have an imaginary school at the equator? So on the equinox, the sun is directly above the equator at the solar noon. So the sunlight, the rays of the sun, would be directly above any location along the equator. So that imaginary school at the equator would have a measurement of 0. There would be no shadows. When Eratosthenes did this experiment, he did it at the solstice. And you might notice, oh, why did he do it at the solstice and not the equinox? Well, at the solstice, instead of the sun being directly above the equator, it's directly above the Tropic of Cancer, and specifically at the summer solstice. So different times of years, it will not always be at the equator, having the sun directly above those locations. So that's why we do it on the equinox and get that measurement of 0 from the imaginary school at the equator. So you can use that value if you're not matched with another school. You can use the imaginary school at the equator. Their angle would be 0 degrees. Okay, so for this collaboration, whether you are actually collaborating with another school or using the imaginary school, you will need to know the distance between yourself and that other school, or between yourself and the equator. So there's 3 options for you to figure this out. The first one is the NOAA calculator. They have another calculator that you can use where you put in the longitude, latitude of both locations, and it'll give you the distance. Important to note when you're using this, just to change the units to kilometers. By default, I think it's in miles. If you're not using another school, and you're just using an imaginary school at the equator, you can put in your longitude and latitude. And then for the second option, you put in your longitude again, but change the latitude to 0. Okay, and then another option is using the National Geographic Map Maker. So this website is basically just a map of the world. You use the measuring tool, which is on the bottom, and you can click your location, click another location, and it will give you the distance between them. The third option is using Google Earth, a similar tool where you take their measurement feature, you click on your location, you click on another location, and it'll give you the distance between them. We do have a little tutorial explaining how to use Google Earth's measure feature. Oh, well, I will just click through that. I do see a question. So it says, if we do have 2 schools at the same location, or 2 schools at 2 locations within the same longitude, is it okay to do it not during the equinox? That's a great question. Let me think about it as I keep going, and then I'll answer it towards the end. Yeah, I'm gonna keep going through the steps, and then I'll answer your question at the end. Or CJ, who's been answering questions and sending links in the chat, if you've got a second to answer it, that'd be great. Otherwise, I'll take that at the end. Okay, so the next step after you find the distance between the 2 locations and are using the data from another location, you'll want to calculate the circumference of the Earth. And the way to do this is to compare your little angle difference to the entire circumference, or the entire circle of the Earth. So you want to take your angle and the angle from the other location, and you find the difference of it. You just want the value of that difference. So if it comes out being negative, scrap the negative, it's just the value. So you find the difference, then you divide it by 360 degrees, because that would be a full circle. And that fraction, again, it equals the distance between the 2 schools divided by the circumference of the Earth. So the circumference itself equals 360 times that distance between the 2 schools. divided by the difference between the two angles. If again you're taking your imaginary school from the equator as your second location, they would have an angle of 0 degrees. So instead of doing the difference where it's from one school, the angle from one school minus the angle from another school, the angle from the other school would just end up being 0. So it's just the angle you calculate divided by 360 equals the distance between your school and the equator divided by the circumference. So rearranging that a bit, you get the circumference is equal to 360 times the distance between you and the equator divided by the angle you calculated. Okay, lots of math. If you're not a fan of math, or you're teaching young students, or you're not a math teacher and you don't want to go into in depth on that, that's totally okay. We do have a Google Sheet calculator for you, where you just input your measurements and it'll do all the calculations for you. So to use this Google Sheet, you'll have to save a copy to your drive, or you can download it as an Excel sheet, and then you can put in your measurements. So you measure the height of your stick, you input that value there, measure the length of the shadow, you input the value, you get the angle. The angle will carry down into this second section. If you are working with another school and you're within the same hemisphere, so you're both in the northern hemisphere or you're both in southern hemisphere, you will input the angle for the collaborating school. Your angle from above will carry down, and then you'll input the distance between the two schools, between your school and the other school, and it'll calculate the circumference as well as the error percentage from the actual scientific value. If you're working with a school in different hemisphere, like in a different hemisphere, you're in the northern and the other school's in the southern hemisphere, don't worry, just use the other option on the right side. If you are not working with another school, you're not collaborating, you're just using data from the equator, so you're assuming 0 degrees. So you will input the distance between your school and the equator. Again, the angle will carry down that you did the calculation of, and it'll calculate the circumference for you as well as that error percentage. So I explained the spreadsheet, but seeing it work is the best way. So here is how it looks with values. So these are values that the director of Discover the Universe, Julie Bolduc-Duval, these are her measurements, and she collaborated with a school in Colombia. And so she measured her height of a meter stick is 100 centimeters. She measured the length of its shadow, which was 103 centimeters, and she got an angle of 45.8 degrees. The angle for her collaborating school was 4.2 degrees, and the distance between the two schools was 4,619 kilometers. And using all of that data, all of those calculations, she was able to get the circumference of the Earth within 0.37% error. So it was extremely close to the actual scientific value of the circumference of the Earth. If she hadn't collaborated with another school and she just wanted to do this calculation without another value from another school, so assuming she's taking that 0 degrees from the equator, she inputed her distance between herself and the equator. So that was 5,127 kilometers. And again, the angle carried down, and she was able to get the circumference within, again, 1% of an error percentage of the actual value. So it was 0.46% again. So this is a very accurate way of calculating the circumference of the Earth. And again, the spreadsheet will do it all for you. Okay, now going a bit more into the collaboration, so the Eratosthenes Experiment International Collaboration. This year's one, this time around, will be on September 23rd, 2024, so the day after the equinox. It is a Monday, so you can do it with your school. and the registration is open. And again, this is a great way to get the other value from another school at the same longitude, and to do these calculations. And the link is on the slide. Again, CJ's been sending the links, so you can access these slides through the link he just sent. But also, I'm pretty sure he has sent the link to this collaboration earlier as well. Thanks for sending the link. So far there's only a few people who have registered, but leading up to the day of the equinox, there will be more people that keep registering. If, like, for myself, I'm looking at Toronto, I would probably match with this school in South America to do this experiment. So it is a great way to collaborate worldwide. If you want more resources about the Eratosthenes experiment, you can go to their website, click on lesson plans, and look at the resources. You can also watch the video with Carl Sagan, where he explains this experiment. He does the little bending of the paper to see how the shadow changes. And it was a really good video. I loved watching it. Okay, so that's it. Let me know if you have any questions. Yeah, I see that CJ has answered the question in the chat. But if you do have any more questions, please feel free to send them in the chat or unmute yourself, and I'll happily answer them. And I'll just show you the last slide. Yeah, so if you have any questions, if you're thinking about it and later tonight you're like, oh man, I should have asked this, don't worry, you can send us an email. We have our info@discovertheuniverse.ca email. You can reach out to me or any of the other people working at Discover the Universe. Yeah, and you can access these Google Slides through the link and the QR code. There is a hand raised.
Yeah, hi, I'm from Montreal.
Hi.
Thank you. This is really cool. I'm going to do it with my students. What I was wondering was, since we're pairing with a school on the same longitude, is there a way to find out what the circumferences of the Earth at that particular longitude as opposed to the equator?
That's a great question. I'm not actually sure.
Because that would be, or you just have the discussion about, you know, that's where your percent error might also come from, because you're not comparing.
Yeah,
so I was just curious. I think I'll do it regardless, but like,
yeah,
I was just
that's such a good question. I'm not 100% sure, but any of the discrepancy between the measurement of the circumference of the Earth would probably fall within that percent error, and that's why the percent error itself exists.
Yeah. Okay. All right, cool. Thank you very much.
Yeah, for sure. So CJ just said in the chat, you can raise your hand or ask questions in the chat for sure if you would like to ask. Also, you can just unmute yourself. Also, these slides are available for you to use if you would like to bring them into your classroom or use them for reference later. You absolutely can. You have the link. The link is on the slide. CJ sent it in the chat. There's also the QR code. I see again, there's another raised hand.
Yeah, okay to speak? You can hear me?
Yeah, I can hear you.
Yeah, the question was just about whether the circumference being measured is, you know, I mean, the Earth is a flattened spheroid, so it will depend which way around you go on the circle, what kind of measurement you get, I would imagine.
I think like it
The
isn't.
equatorial circumference, I think, is bigger than the longitudinal one.
Hmm. I don't know specifics on that, but I think it is so close to being almost perfectly spherical that any discrepancy would, oh, CJ's got his hand raised, that any discrepancy would probably fall within the percent error. But CJ would probably know best. Let's hear what you have to say.
No, just kind of stating that yes, the Earth has different circumferences depending on exactly which way you slice that sphere. And of course, as is raised by multiple people in the call already, that what specific longitude you're measuring along versus the equator circumference, that is going to be different. But the reason why we included a scientific percent error value was to kind of inspire those conversations, especially in older students around, well, why don't we have this exact value that's kind of reported that you normally see that's reported? And that's part of the conversation. The Earth isn't a perfect ball. And then you can actually talk about that a little bit. Other things are like you've got maybe a measuring stick that isn't perfect, or your measuring tape that you were using to measure your stick or your shadow was off by a millimeter here or there. And so that's kind of why we have it there. Not so much to say that, oh, look how much you were wrong, but more so to inspire the conversation on there is error in measurement and things aren't usually perfect spheres floating around in space, including the Earth.
Yeah, go ahead again. You can, if you have more to say.
Okay, yeah. I guess the thing I guess concerns the error. I think there's always a danger, and I feel that the high school textbooks don't do a good job of that. When you say percent error, and compared to a so-called scientific value, it always assumes that somehow the scientific value is the correct one, where in fact the errors should be calculated from the measurements that you make yourself, and then they should. And if you've estimated your errors accurately and done the proper calculations, they should fall within the range of the scientific value, so-called, which is also subject to error, but presumably much smaller ones. Hope I'm making sense.
I think you're making sense. I think the idea of the percent error is to start a conversation like this where like where are we identifying the error? So the measurements that you're taking, the error could be again in the rulers that you're using, the length of your stick. It could be in the fact that again, the Earth is not a perfect sphere. The scientific value does have some sort of error bar to it and has some sort of uncertainty to it where yeah, we've measured the circumference of the Earth, but there will always be some sort of uncertainty, so any values that you measure should fall within that. But in this experiment, when you're taking it to your students, there's other things that would impact the error that you would get. So like it would be like there's human error involved, there's the what tools you're using to measure it, but there's also the physical physical part of it where the Earth is not actually perfectly spherical. So I think what you would want to lean towards is just the discussion of why error exists in the first place in both your measurement and the actual scientific measurement.
Yeah, no, I agree completely. My biggest concern is just that people understand that there's no exact value, that all the measurements that we make, whether they're made by scientists or by teachers or by students, are all subject to error. That
For sure.
errors we make as students are likely much larger than the ones made by a scientific team, but the errors are estimated from within the experiment, not by comparing it to some canonical result.
Yeah. So in this case, we're comparing it to the calculated circumference, the one that is accepted as the circumference of the Earth. But within that circumference that we're comparing it to is an uncertainty of itself. And that's that's a great way. That's a great thing to talk about as well. And I do see what you mean, where the error that we would want to calculate of our the error on our measurements is based off of the errors that we would make in the measurements that we're doing. So instead of having uncertainty being compared, like the error percentage being a comparison to the actual value, it would be based off of like the precision of your measurement tools and so on. In this case, the way that we've framed the error percentage is more of to spark a conversation about why the measurement that the students did or that you did is different from something that was measured by scientists across the world, or like is the accepted value of the circumference. So I see what you're saying about how the error on the measurement is not error in comparison to the accepted circumference, and it should be more about like the measurements, your like the measurement tools you use, and like human error and all of that side of it. But again, reiterating for the context of this, like the error percentage on our Google Sheet, it is to see why the measurement that you did might be different from the accepted circumference of the Earth measurement. Did that make sense? I can clarify more if you need.
No, it makes perfect sense. It's really a beef I have from
Yeah.
textbooks where they make this. I mean, it's really a comparison with someone else's measurement, not an error calculation.
Exactly. Yeah. It is the comparison rather than where the error lies in like your measurement or the experiment itself. Yeah.
Thank you. Thank you.
Yeah, for sure. If anyone else has questions, feel free to unmute, put your hand up, put it in the chat. Thank you so much. Thank you all for coming. If you need to head out, go for it. If you think of a question later, please feel free to send us an email. Thank you all. Are there any outstanding questions? Claudia or Michael, any questions you have? Okay, awesome. Thank you.